So for this question, we are looking at buffers and buffer calculations. If you take a read through it, there's lots of information on here, and I'm going to try and break down where that's used as we go through. So to begin with, we are going to work out the concentration, the hydrogen ion concentration within the buffer solution. So I'm trying to lay out all of the working out here. We're going to do that by 10 to the negative pH, 10 to the negative 3.87, giving us the value 1.3489 by 10 to the minus 4. Now, we are going to need to use the H+, but before we do that, we need to take our Ka expression and we need to rearrange it to make CH3COOH concentration the subject, because it's that concentration that we're actually going to want to work out. At that point, it's about putting all of the data in to this expression in the right places. Now, as you can see here, what I've tried to do is highlight precisely where those numbers have come from. So we were told the concentration of ethanoate ions, that's highlighted in yellow. We were told the Ka value, 1.74 by 10 to the minus 5. So we've got that one highlighted in blue, and highlighted in green, the concentration of H+ that I've just worked out can go in to this expression. Once we do all of that, we get the answer. You can go through with the calculator to check, but you will get a value of 1.05 to 1.06. Anywhere within that range is acceptable, but actually it has to be to three significant figures. So it's going to be one or the other. Then we move on to 2.2. We are still dealing with buffers. And 6 marks here, so that's giving you a measure of just how big this calculation is. I think it's important to always look for the easy wins when you're doing a calculation like this and see what calculations you can do at the most basic level. Now, as an example, we have got here moles of CH3COOH. We have a concentration and we've got a volume. We've got 500 cm cubed that I've converted to dm cubed here, 0.5. So I can go through and I can calculate my moles of ethanoic acid and my moles of ethanoate ions. Now, as we move through, I've then got to work out what's going to happen after addition of the sodium hydroxide. So when I add my 7 by 10 to the minus 3 moles of sodium hydroxide, I know that that's going to neutralise my ethanoic acid. So my ethanoic acid on a 1-to-1 mole ratio will go down by that amount, and I have the new figure. Similarly, I can look at what happens to the CH3COO minus. That will go up by the 0.007, and that's because you are breaking apart the ethanoic acid when you neutralise it. So I've now got my 2 new molar quantities. Now, when I move to the next stage, I need to work out what my H+ concentration is. So to do that, I'm going to rearrange my Ka expression, and I get H+ as the subject. Moving over to the other side now, because I'm running out of space. The Ka was provided before 2.1, so that can go in. And you'll notice I've taken my moles, but I don't want moles in this, I want concentration. So that's why I've got the 0.123 divided by 0.5, and similarly the 0.0675 divided by 0.5. When I put all of those figures into the calculator, I'm going to end up with an H+ value of 3.162 by 10 to the minus 5. I'm then going to do my log calculation, so negative log to the base 10 of that H+ concentration, giving me a pH of 4.50. And the 0 absolutely must be there, highlighted in green. We're linking it back to the fact that the answer is to 2 decimal places as requested.